Hello, everyone. I hope you can all hear me when we complete this webinar. Okay, yes, we can start and people will continue to join slowly. And while I'm doing a short introduction, so yeah, today we have the chance to have to welcome Hicham Badri, so co-founder and principal chief scientist at Mobius Labs. We like to say at Pruna that he is also the GOAT of kernels. So looking forward for the presentation that we'll do, Isham. So I just let you the stage, and yeah, please go ahead. If you have any questions, ask in the chat, and we'll take them for sure at the end. So Isham, stage is yours.
Yeah, thanks so much, Bertrand, for the introduction. So basically, today's talk is about MXFP quantization and basically how to use it in Triton. As you know, MXFP quantization is a really, really hot topic right now, and everyone is trying to make it work in the industry. So people are trying to train models with, but it's actually not that simple to work with this MXFP format. So basically, the goal of this talk is to share with you what I have learned, working with this format, just understanding how the MXFP format works and how to implement MXFP Triton kernels. So we are going to talk about activation, quantization, GMNs, and stuff like that. So yeah, I mean, let's start. So overview. So I'm going to start with the introduction. Then we are going to talk about the standard, the MXFP standard format. We are going to talk about difference between MXFP4 and VFP4, what is really the deal with these scales, and what is the difference of the D types of the scales that's made it the big difference between the MXFP4 and VFP4, for example. Then we are going to jump in. We are going to talk about Triton implementations. I'm going to talk about activation quantization in Triton because it's very, very important to have good activation quantization kernels when you're working with MXFP quantization. And then we're going to talk about matrix multiplication in Triton using MXFP. And then obviously we're going to finish with Q&A. But so please stop me if you have any question. I think it's better to, if you have a question, just stop me. But I cannot see anything in the chat. So Bertrand, if there's a question, can you please stop me and we can address that?
So
yeah, I mean, as everyone knows, machine learning models are getting very, very large, and hardware is extremely expensive. So if you want to deploy a DeepSeek model, you need 8 H200s at least, and so you cannot even fit it in one node of H100s. And obviously models are getting even bigger, and obviously the challenge is how to deploy these models for cheap. So we don't want to spend a lot of money deploying these models, and especially true for GPU poor people. So not everyone can afford a DGX B200. So one DGX B200 costs 700,000 euros. So so basically, what can we do about this issue? So obviously the main solution for this is quantization. So I suppose everyone is familiar with quantization, and especially for deploying LLMs. So in transformer-based models, basically quantization is used in many levels. So obviously you can quantize the linear layers, you can quantize the attention models, so you can quantize the KV cache, and obviously you need different types of quantization for different applications. So if I can summarize all of this, you basically have two use cases where that you need to think about. So if you're memory bound or compute bound, and when you're memory bound, so that's typically the case where you're serving, let's say, one user on, let's say, one GPU. So you're memory bound in this case, all these quantization methods that you're familiar with, like the stuff in Goof, for example, or GPTQ, HQQ, stuff like that. Those are techniques that quantize only the weights, and they are great when you're memory bound. But like once you start to deploy models at scale and you have like millions of requests, then you're really compute bound, and you start to think about like different type of quantization where you need to quantize the activations, for example. You need to quantize the attention modules, and this is like really the bottleneck when you try to deploy models on a large scale. So the type of quantization we are gonna talk about is merely interesting in this type of scenario. So if I can summarize this slide, it's basically transformers plus quantization is basically two things. It's less VRAM and making things faster. So why is quantization important for compute bound scenarios? So there's a kind of rule that if you divide the bit width by 2, you get 2x speed up in terms of flops. So this is in theory, basically. So if you go from, let's say, FP8 matrix multiplication, so the activations are FP8 and the weights are FP8, so both they need to be the same data. Then you go to FP4 by FP4. This in theory should be 2x fast. So basically, you reduce the bit width by 2, you get your x speed up. It's pretty. And also what we notice again is with each iteration of the, like in the each iteration we get faster flops. And the interesting thing is mainly in the Blackwell iteration. So if we compare the RTX 6000 Ada and the RTX Pro 6000 Blackwell, you can see that like running FP4 with RTX Pro 6000 is about 2.8x faster, but it's only 1.22x the price. So it really actually makes sense to upgrade in this situation, to upgrade to actually use the RTX Pro 6000 to deploy with FP4, because it's just like makes more sense. It's like cheaper and faster. I mean, now the challenge is actually how to deploy stuff with FP4. So there's a lot of work on this. So we are not going to talk about like how to train models with FP4. It's like a whole different story. What we are going to talk about is mainly understanding like what is this FP4, what are the different FP4 formats, for example, and how to deal. Do you have any questions so far? So before like jumping in,
maybe one quick question is, you mentioned weight and activation quantization. Do you have a rule of thumb or practical, rule that you have considered to switch from weight to activation quantization, or vice versa, Drew?
I mean, so like as soon as you get compute bound, you need to quantize the activations. That's like, you cannot, like if you keep the activations FP16, you will not get any speed up. So because like the tensor core operations, like the speed up in tensor core operations, they come from having the same data from the flops. I mean, loosely speaking, because you can do MX, like we're gonna see it later, because like you can do MXFP8, for example, by MXFP4. You can mix dtags, but in general, like in order to get the actual flops speed up, like you need to actually quantize both, because otherwise you're like, if you're not quantizing the activations, you need to actually dequantize the weights, and you will do the matrix multiplication with the higher dtag. So for example, if you're doing 4-bit weight only and your activations are 16-bit, you actually dequantize the weights and you do matrix multiplication with FP16 actually. So you're only gonna get the speed up like when you're memory bound.
Makes sense. Thanks. There is another question in the chat. So what are some of the challenges with FP4 compared to FP16? And
yeah, we are gonna talk about that later. Yeah.
Okay.
Yeah.
Then I guess we keep it for later.
Yeah. Makes sense to talk about that later. All right. So what is this MXFP format? So it's basically a new quantization format. And so the thing here is that for a long time, when people started to quantize models, like especially for LLMs, the quantization setup was not standardized. So everyone was coming up with their own format. So you have like people using like a lookup table, other people just using like linear quantization. So MXFP format is actually standard. So like many different companies in the industry, they gathered together and they said, this is standardized. So this is what we are going to use, which is great because like it simplifies many, many things. So so it follows the called microscaling specifications. So basically using block size 32 and using 8-bit scales. So this E8M0 scales, we are gonna talk about it, but for now, just keep in mind that think about it as a normal quantization, like a GPTQ or HQQ or whatever. It's just that the block size is smaller, like 32, and you only have the scales, and the scales are 8. So later we are gonna see like what kind of 8-bit scales, like what is this E8M0 scales. We are gonna explain it a little bit more in details. So the other thing about the MXFP format is that it allows mixed precision. So you can actually do stuff like you can do MXFP8 activations with much more with the MXFP4 weights. So you can do that if you want. And obviously, like you can do, it supports like FP4 and it supports FP8, it supports FP6. And then here, like in this table below, like you have a screenshot from like the official specifications. It just tells you like, you see like all of them, they are using block size 32 and all of them, they are using this same scale D type, which is this E8M0. And the only thing that changes is like the weights, quantization weights, which is like, could be FP8 or it could be FP6 or FP, right? So there's another format which is called NVFP4, and it's Nvidia's adaptation for MXFP4. And the difference is that they use a smaller block size. They use 16 instead of 32. And they use a different, so they use float 8 scales. There's a good reason why they do this, because it's much more accurate. So pretty much like on NVIDIA, everyone is using NVFP4 because it's just more accurate. But this is only like NVFP4 is only for NVIDIA GPUs. So like there's no NVFP4 on AMD, but there's MXFP4 on AMD. And so basically how it works is that you have your float activations, float weights, which are matrices, and basically you quantize them and you get scales and you get quantized weights. So two testers per reference data point. And basically when you do this tensor core operation, you would do the dot product between the matrices and it's going to multiply the scales. So that's basically what it's doing. It's not too difficult.
Maybe there is a question in the chat.
Yeah.
And so one question is, do different bitwidth formats still use the same underlying MMA for matrix mul and accumulate instruction in Triton, CUDA, and so on?
That's actually a good question. So I have a slide about this. So I'm gonna get back to it because it's a little bit complicated, but it's different instructions. Anyway, it's a really good question. I'll get back to this because like I need to explain a couple of things before jumping in.
Good.
Yeah, but that's actually a good question. If I forget, I mean, there's a slide about it, like, but if I don't answer your question, please stop me in that slide so I can answer exactly your question.
I think you're muted now, Hicham.
Sorry about it. So let's get back to the classical quantization that everyone is hopefully familiar with, like stuff like GPTQ, NWQ, HPQ. Basically, what we do is that we take the weights, and there's some magic, and there's a magic algorithm, and we get this WQ, S, which are the scales, and Z. So Z, if you are asymmetric, and if it's symmetric quantization, so there's no Z, right? And here in this case, the WQ could be int 8 or int 4 or int 3 or int 2, doesn't matter. The main point here to understand is this kind of quantization is not like native quantization when you do matrix multiplication, meaning that when we are writing our Triton or Catalyst kernel or CUDA kernel, we are actually dequantizing these weights on the fly, and then we are doing matrix multiplication with FP16. So that's why like these methods, they are great when you're memory bound. So like when you're just serving like few users, like few requests, it's typically about size 1. They are really great in that situation, but you cannot really use this to get any speed up like for really large deployments, because like the actual blocker here is the compute, and we are actually traditionally we are doing matrix multiplication in FP16. So this is very important to understand. So now the big difference is that in MXFP, the MXFP format is that we actually have native support. So basically the tensor core matrix multiplication is actually taking in the actual quantized weights directly, and it's also taking in the scales. So that's why it's actually native support. That's why we can actually do FP4 by FP4 and actually get a huge speed up. And so essentially, if you compare both, they are very, very similar. It's actually the grouping logic is also very similar. It's just that before we were having integer quantization, here we have floating point quantization, and it's symmetric, so there's no 0 point, and the scales, they are 8-bit scales. While in the normal, like the regular quantization, we will use floating point, like FP16, bfloat FP16, or even float 32 for the zeros and the scales. And the main difference here, again, because I mentioned this before, all the MXFP formats, so MXFP8, MXFP6, and MXFP4, they all work the same way. So they're all of them, they have group size 32, and they have E8M0 scales that I'm going to explain later. And NVFP4 is pretty much the same. It's just that the group size is 16, and the scales, they have a different beat. That's pretty much. It's not too crazy. Okay, so now we are gonna talk about these scales, because that's actually the big difference that might confuse a lot of folks. So these scales here, they are 8-bit, and they take the form of E8M0. So E8M0 is a very weird 8-bit format. So it's basically just exponent. So there's no matches. And this is basically representing just powers of 2, okay? So you can represent values between 2 to the power minus 127 to 2 to the power 127. So the range is extremely large. But it's like, I mean, it sounds nice on paper that the range is large, but it's actually most of the range is completely useless, because when you're quantizing weights, like if you take like weights from a real model and you take a look at the scales, they tend to be actually very small. So you're actually using a tiny fraction of this range. And that actually creates a lot of issues with MXFP4. Like the quality is not really good. A lot of people are complaining about it. We actually have done some work on improving the quality of MXFP4 quantization weights with some some calibration / training approach. But in general, the issue is that since you're only limited to powers of 2, like you cannot really represent these scales properly. And that's why Nvidia came up with this NVFP4 format. It's exactly for this problem, because like the quality was too bad. So they said like, let's do something different. So the difference is that, as I said, in NVFP4, you actually don't have E8M0 8-bit scales. We have actually E4M3 scales. So E4M3 is the typical float 8. The only difference is that they are positive, so that's why you have U. So it's assigned, and it also uses a lower group size. So if you're using Nvidia, there's really no point in using MXFP4. Like you just use NVFP4 because it's more accurate. It's slightly slower than MXFP4 because it's like a really tiny bit slower, because you load twice more data in terms of scales because you're using group size of 60 instead of 32, but like the quantity is much better. But of course, like you can make FP4 work, like if you're like doing some heavy post-training quantization. Like that will be like really useful if you wanna release a model and you want people to use it on AMD or Nvidia, because if you just release a model that works only with NVFP4, like you cannot run it on AMD GPUs for. So we talked about the D type of the scales. So now let's talk about the detail of the weights. MXFP8 is quite and the weights are FP8, so it's the regular FP8. But for the FP4 format, it's basically 16 values. And as you can see on your screen, it's between -6 and 6. So there are two things that we need to do, obviously. So the first thing is that once we get these values, once we map our quantized values into this range, -6 to 6, we need to do two things to actually use them, because we need to pack them. And in order for them to be represented as MXFP4, we need to do some post-processing. So the first thing that we need to do is, so if we want to do bit packing, we need to work with these integers. So the first thing that we need to do is to map this -6 to 6 to uint8 indices. And the way how to do this is that there's this specific order that you need to follow that I put here on the screen. So this FP4 index, you see that you have 0, 0.5, 1, 1.5. So this means that index 0 is 0, index 1 is 0.5, index 2 is 1, etc. So it's like a lookup table, you know, like, so 0 would be 0, 1 would be 0.5. So you need to do this mapping. So once you do this mapping, which obviously it's lossless mapping, once you get this mapping and you get your 8 indices, you need to pack them. And the packing is basically just interleaved packing. So that means just successive values are packed. Every 2 successive values, they are packed as uint8. So pretty standard, like everyone is using this interleaved packing. So there's like nothing nothing like out of order here. It's just that there's these 2 steps. First mapping to indices, and then like you do the bit packing. And the bit packing is like regular bit packing. It's nothing crazy. Okay, any questions regarding this? Because now I'm gonna talk about the instructions, like.
So maybe I see there is someone typing a question, but I have a question in the meantime. So you mentioned the scales. So you mentioned the reason is to switch like to these different data types is because most of the scales are actually of low values, kind of. But you mentioned also this other difference, which is the group size. And is there any reasons for this difference for the group size between MXFP4 and FP4?
So question is about difference between MXFP4 and FP4. So the main problem is that the range of the scales in MXFP4 is just powers of 2, and you cannot accurately represent small values with this. It's like literally you are only using like maybe 10 values out of the whole 256 values. It's a bad choice. It's a bad D-type for representing scales. So if you just take weights and you just quantize them like MXFP4, like the quality would be very bad. So there are ways to recover quality, like you can do post-training quantization. But if you're using Nvidia GPUs, they have this NVFP4 format, which uses the FP8, you know, the regular FP8 D-type for the scales. But there's also a problem with that that I'm gonna talk about later. So both of them, they have issues, but the issue with NVFP4 you can easily overcome. Yeah.
Maybe one question is, you mentioned also like NVFP4 is slightly slower because of the group size, which is
yeah. I mean tiny bits. Yeah. So to clarify, like it's just a tiny bit slower because the scales, the way the scales are loaded is really optimized. Like it's really, if your kernel is really, the pipelining in your kernel is loading all the stuff like properly, really optimized, like you're using like the whole maximizing the bandwidth, like to load things as much as possible. The only blocker is basically the loading the scales, which is like a tiny bit slower, but like it doesn't really matter because like the quality is better.
Okay, makes sense.
Yeah.
There are 2 questions in the chat. So one is uint8 a standard for bit packing with MXFP4?
Yeah,
Oh.
yeah, yeah. So for that question, yes, at least in Triton, that's how.
Okay, so the next question was, can we do it also with U int 16 with 4 values packed instead of 2? But I guess, yeah, good.
I don't think so. Because like the instructions, they expect the tensors to be in a very specific format. Like you cannot. I mean, there's like it doesn't change anything. Like in theory, like you could like changing the bit packing doesn't really change much. But like the tensor cores are actually expecting values in very specific format. And in Triton specifically, it's uint8 packed, and I think also in Cutlass, I think it's also. I mean, it's uint8, but it's like a float for view D type of uint8, so it's still using uint8 packing.
Okay, which yeah. Another question is, what is the point of the packing? Is it just the interface to the instructions with which then unpacks them?
I mean, yeah, packing is a very standard thing used like everywhere in a quantization, not just for MXFP, because the answer is that there's no native sub-byte D type. Like for example, in PyTorch, like the lowest you can go is int8, for example, right? Or float8. So there's nothing like int4, for example. So in order to do that, like in order to actually have 4-bit stuff in memory, we need to do what is called bit packing, which is basically we take, let's say, two 4-bit values, and we put them in one 8-bit value, which is a lossless transformation. Is very efficient. So that's basically the point of bit packing. It's basically like we want to actually, if you want to actually have stuff in memory as 4-bit, like this is the only way to do it. Like you need to do bit packing. You can put like you can like bit pack stuff in 1-bit, 2-bit. The logic is always the same. You just like put different values in one byte, for example, or you can use in 32 packing, whatever. If that answers the question.
I think it answers perfectly. Like everyone says, thanks a lot for the answers already. So there's no more question now. So please, you can continue.
All right. So now the question about the enemy instructions. So now we are this is getting interesting. So it is interesting and very confusing, because so normally, like in GPUs, like when you have a new generation of GPUs, like usually they would use like the same instructions. But this is actually not the case for Blackwell. So for Blackwell, they separated the B200s like SM100 and SM120. So they don't have the same instructions. So that's actually a big problem, because and it was one of the reasons why we started doing this work, is because in Triton they have MXFP4 support, but they only have it for the B200. So which means that the kernels that work on the B200, they don't work on the 1590 and 6000 RTX Pro, because they don't use the same instructions. So instructions for SM100, they use this TC Gen 5 MMA, and the ones in SM120, they actually use the regular MMA sync, but they have a new identifier, which is this blocks. So this is the first difference, is that Blackwell SM100, Blackwell SM120, they are very different. The second question, which actually would the second answer that answers the actual question about like is MXF8 and MXF4, they use the same instructions? Yes and no. So yes, they are, for example, like the first instruction is MXF8, F6, F4. You can actually do MXFP4 with it, but it's actually half the speed of the other one. So the first instruction, this MMA sync, let's say for example this MMA sync aligned kind, and then you have MXF8, F6, F4. This is the mixed precision MMA. So here, like, you can use it for MXF8, you can use it for MXF4, you can use it for MXF6. But to actually get the speed up for MXF4, you need to use either one of these. So either the MXF4 block scale, or you use the MXF4 Nvidia. So I hope that answers the question. Which is basically the same for also TC Gen 5. Why did they do this? I honestly have no idea.
To make things more complicated. I guess. Okay, there is another question. So maybe I can read it up like if I have access to an Nvidia A40, doesn't support NVFP4, the only way to test my model is to do an emulation of NVFP4 for accuracy and analysis.
Yeah, correct.
Yep, okay.
Yeah, and that's already supported in Triton. If you try to run, so let me correct this. Sorry, that works for MXF8 and MXF4. Like if you try to run MXF4, it will actually run in simulated. It will do FP6. If you try to run NVFF4, it will actually crash. So, but MXF8 and MXF4 they actually run in simulated, which is pretty slow.
Okay, makes sense. And last question. I think, or is that a question? I guess it's more like a comment. The SM100 uses to install memory for accumulation.
Yeah, they work differently. But the point is that it's a bit confusing to call them both Blackwell, because like for anyone who is familiar with like the Nvidia GPUs generations, they would expect that okay, same generation, they would use the same instructions, but it's actually a surprise that it's not actually using the same instructions. So like if you try to run like so like there are some kernels available like for B200. So if you try to run the B200 kernels on 5090, it's gonna crash. So and the reason is that they don't use the same instruction.
Okay, makes sense.
All right. So maybe we can move on because we still have a lot of stuff to discuss. All right. So now we are going to talk about Triton. I will try to speed run this a little bit because there's really a lot of stuff. So the first thing that we are going to talk about is writing activation quantization kernels. So they are really a couple of things that you really need to watch out here. So let me summarize this. So the first thing to keep in mind is that we are working with these group sizes, and in order to do it properly, like we need to have shapes that are multiples of the group sizes. So if you're just processing requests and they have arbitrary byte size, arbitrary sequence length, you actually need to do some padding. And if you do this very naively in PyTorch, you just take metrics and you just pad with zeros, it's going to be very slow, especially for very large transfers. So what we will try to do is actually to write our kernel in a way that will do the padding automatically in a very efficient. So you do this in a very simple way. You just use some masking, right? Because like the padding, you don't need it for the scales. The padding you need it for the actual quantized weights. Because the scales they need anyway to be multiples of the groups. The other thing is that this is specifically for FP4, because there's this step where we need to go from quantized weights as FP32 to packed weights. We need to figure out a way how to do it very efficiently. Because there's actually, if you don't do it properly, like if you do it like naively in PyTorch, it's actually very slow. So we are gonna also talk about, okay? We're gonna talk about like how to do some magic to make MXFP4 activation quantization like really fast. Yeah, because there are some tricks we can hopefully use. But basically the general algorithm here is very simple. So for MXFP quantization in general, so basically you just, if you had to do it like in PyTorch, you would just resize and you reshape your metrics, right? And you just find the max values and you divide it by the max value. So if you're doing FP4, for example, max value would be 6. And if you're doing FP8, the max value would depend on which type of FP8 you're using. So if you're using E4 and 3, there will be 448. So then you get these scales which are for 32. And then you need to find the next power of 2. So if you're working with this E8 M0 defect that I have explained before, because they are powers of 2, like once you get these scales, like you need to map them into powers of 2. So a lot of the accuracy loss actually happens in this step, in this next power of 2. You need to do some clamping because you don't want it to be outside the range for some reason. I mean, it shouldn't be outside the range because the range is really huge, but just in case, putting it there. And then you just like divide your weights by the scales. You need to make sure the scales are not too small, so you don't divide by 0, by the way. And then basically this step scales to torch float 8 E8 M0 is just like casting operation. And in Triton, it expects a uint8, so you can just do a few of torch uint8. So the scales at this point, they are actually just storing the exponent plus 127. So I think I have explained it before. So like it's very simple on the PyTorch side, but there's a lot of stuff missing here because like there's no padding. So this, if you want to contest the weights, this could be like a nice piece of code to do it. But like for activations, as I said, you need to do some padding, blah, blah, blah. So, and for FP4, as I said, like we need to do the packing. We need to do the mapping to the indices, and we need to do the packing. All right, so let's go ahead and take a look at this kernel. So this kernel is very simple. It's doing MXFP8 activation quantization. So basically what I did here is that I'm loading. So the first part is just loading blocks of size, block size, M, group size. So the reason why we want the second dimension to be group size, so we can use TL max with axis 1. So you can actually have the max over the second dimension, right? Because that's basically what we are looking for. So because we want one scale per group size, right? So basically it's very simple. We load this block and then we do TL max. We get this, we divide by the max one, and then we find this next power of 2 that I'm gonna talk about later. But here, like we need two types of scales. So we need the float value of the scales because we need it to quantize the weights. So this is what happens here. But we also need the actual exponent because this is what we actually store as uint8 scales. So this 2 out d times 2, that will be the, because here, like as I said, it's MXFP8, so like out d type would be just like FP8 format. So very simple. Actually, there's a mistake here in this slide. I forgot to add the masks. We actually need to add the mask in the first TL store. When we store the output, we need to add the mask because, as I said, because we are doing this padding, and if we don't store, like if we store stuff like outside the range, it might crash actually, and we might have like some weird results. So you need to actually add the mask in this TL store just to make sure that especially the mask on the M dimension, because the K dimension is actually fixed. But on the M dimension, you need to add like a mask in here. So there's this next power of 2. We need to do this very efficiently in Triton. And so the thing here is that you can do it with the TL log 2. But the issue is that it's actually a bit slow to do it with TL log 2. And the reason why is that if you use TL log 2 and you compile the kernel and you take a look at the PTX code, you will see that the compiler will actually use a polynomial approximation of the log 2. And you will see that actually, like it's huge, actually, it's like a lot of polynomial approximations. So there's a more efficient way to do this. So there are 2 ways to do it. So you either write PTX and you actually force it to use log2 approx, which is like a more efficient version of TL log2. Or you can just do some bit op gymnastics and just try to figure out like how to do it just with bit ops. And that's my default implementation. That's what I would use. They are kind of the same speed, but like the bit op one is actually, it gives you exactly like the next power of 2. On the other one's actually doing some more approximation. But it's, I mean, like you need actually a good cup of coffee to not screw up this bit ops and do it properly. And actually, I didn't put the right code here. This one is actually I should return the exponent here because like you don't have to actually do minus 127 and then add 127 later. You can just return the exponent, but yeah. But pretty much like the logic is exactly like this. Then you can just do some bit ops to do the next power of 2, and you can have like a more efficient next power of 2. So now the fun stuff. So now, like on top of that, so the kernel. So if we want to do MXFP4, so if we want to take this kernel, which does MXFP8, and we want to do MXFP4, we need to do some additional steps. So it's mainly happening here in this out. So when you get this tensor divided by scales, and you get this out tensor. So we need to do two things. So first of all, we need to map the out values to the FP4 range, which is -6 to 6. So it's these values here. So actually, to do this properly, you need to do a small trick. So essentially, like if you do it in PyTorch, you would do something like this. Like you would do a lookup table, which is very inefficient. Just a small parenthesis, there's a way to do it efficiently in PyTorch, but I'm just putting this here, like this is a naive way of doing it in PyTorch. This is basically like looking for like the closest value in the FP4 values. And basically, for example, 0.1 would be mapped to 0, -5.8 would be mapped to -6, you know, like you just like put it like to the closest beam. But we cannot do stuff like this in Triton. Like we need to do it in a very efficient way. So is there a way to do this in Triton? And actually, there's a way to do it. So there's this trick that you could use whenever you need to map values and you have increasing values. So for example, we need to do a lookup table, but your table is actually sorted in increasing order. So there's this trick that uses a pairwise averaging, and basically what you do is that you take the average, you do pairwise averaging. So you take 0.5, so you get average is 0.25, sorry, and then you do the average of the next one, you do the next one, and basically to find the index of your beam is basically just the number of thresholds that surpasses that index. So like you can do it, like literally you can do it in 2 lines of code. So you can just you load this in your Triton kernel. You can put like ethic last because like you want this to say, and then you just like do literally this thing, like you just do sum, TL.sum above thresholds. And here, like as you can see, the order that I put here is not random. Like this is exactly how Triton is expecting you to order to get the index of the FP4 values. So here, like the first part, 0, 0.51, 1.5, blah, blah, blah. So 0.6. So that's the first 8 values. And the second 8 values, it's exactly the same thing as the first 8 values, but they are negative, right? So basically, you can just do it with the ADS, right? And then once you get the indices, if it's negative, you just add 8. So this is really efficient way to do the lookup table. But it's not like exactly the same, because you might have an issue when this TL ABSW equals exactly the threshold pause. Then you have an issue. But like you can do some tricks, like you can add like a really small value to make it not equal. You can add some random values just to disturb it like a little bit. But basically, the most efficient way I found it, that I found to do this, is basically with the pairwise average. I think also there's like there's a PTX instruction to do something like this, but I didn't play with it so far. I just did it like in pure PyTorch. But I think there's some PTX instructions that help you to do this. If all right, I'm gonna speed run this because we only have 10 minutes left. So MXFP4 activation quantization. So very similar to MXFP4. The only issue is that the smallest value that we can represent for MXFP4 is actually 0.015625, and that's way too large for small scales. So this is the problem I mentioned before. I said that MXFP4 also has a problem. So the issue is, if you just do it naively, if you take like an MXFP4 kernel and just replace the D types, it's not going to work actually. Because what would happen is that you would have scales that are very small, and then you cast them to float 8, so E4 and 3, and you get none values because it will be outside of the range. Because the smallest value is 0.015625. And if you get like something like 0.001 and you cast it to float 8, it's going to give you a none. So one thing to keep in mind is that whenever you're working with float 8, you always have to make sure that it fits the range. Otherwise, like if you do the conversion, you would get non-values. So like the trick to solve this issue, sorry, is it there's a second scaling factor. So basically what you do is that you get all the scales as for 32, and then you calculate the max of all of them and uses the max to normalize the scales, and then you quantize them to FP8. So this is what, like if you're reading some blog posts by Nvidia and they are talking about MXFP4, they will mention this 2-level scaling approach, and basically this is it. Like you have like block scale level and you have a global scale, which is like one single value, and it helps you like mitigate this problem like of float 8 having like a very restrictive range. But like once you do this, like you're fine. The main problem here is that if you want to do this in Triton, you need to do 2 kernel calls, because you first need to go through all the scales and get the maximal value. And then you have the second kernel, which actually uses the max value to do the quantization. But I found 2 tricks to do this efficiently. So the first one is you can actually do this on one single kernel. And the trick to do it is that you save the scales as float 32. And then once you get the float 32 scales, you actually find the max. And then you cast to float 8. But to do this properly, you also need to do like a partial FP8 conversion. It's like a hacky way. So basically all the values that will create problems, we don't cast them to FP8. But the values that don't cause any problem, we cast them to FP8 and then we cast them back to FP32, because we still need to divide by FP. So the second trick I found is actually you can also use the global scale, like a fixed value. It might sound strange, but it actually works. And if you do it, I mean, it's not as accurate as doing it properly, but it actually works, at least with llama models. And if you do it like this, you only need one single kernel call, because like you already have the value that you want to use to normalize the scale. I mean, we don't have a lot of time, so I'm gonna speed run the math mule. It's actually not too difficult. So here I just put the kind of layout that is expected, like when you, if you want to use MXFP4 or MXFP8 or NVFP4, all the same. So you will do this with TL dot scaled instead of TL dot. And basically these are the shapes that it would expect. So M is untouched, but like the K, it's either going to be divided by 1 or 2. So 1 if it's MXFP8 and 2 if it's FP4. It doesn't matter if it's NVFP4 or MXFP4. And basically the same thing for the weights. It's just that it's like the opposite dimension. And for the scales, it's going to be M and the K divided by GS, so the group size. So the group size will be 32 or 16. So 16 for NVFP4. And the only thing that is a bit weird is that the scales are transposed but the weights are not transposed. But the code is basically very simple. Yeah. So let me show you like a very simple kernel that does. So this kernel works with MXFP4, NVFP4, and MXFP8. So it's like the same kernel that does everything. And it's a very simple kernel. So basically here, what we have is just like pointers for A, pointers for B. So these are like the context weights, pointers for the scales. And it's like, it works the same way like as a normal GMM loop. So you load your weights and you load your scales, and then you do TL.scale. So the only thing that you need to make sure here is that the scales and the weights, they are following this format that I have explained before. So if you do that, like it should work out of the box. So one small clarification here is that this is a very simple way of doing it. There's a more complicated way of doing this. There's a 5D layout for the scales that you could use, which would make loading the scales a little bit faster. But I didn't include it here because just it's not really worth it. But just keep in mind that there's a more advanced way of doing this, and there's also the TMA version, so you can replace TL.load with the descriptor load. And there's also a version where you actually have to transpose the blocks inside. I also didn't talk about this, but pretty much like if you do this, you will get pretty good performance for simple GMM. So this is an actual performance with Triton end to end. So this is with the VNNM and Llama 3.8b. And basically we measured the performance from FP6 to MXFP8 and MXFP4. So this is implementing the stuff that I have been discussing here. So the activation quantization stuff and the GMM stuff. And basically what we did is we also had a reference that it's like a dummy version, which doesn't have any GMMs. So we can actually compare the speed up only for the linear layers. And this is what we get is actually very close to the theoretical speed up. So going from 41.40 seconds to 12.1, it's about like 3.6x or something like this. So it's close to 4x. And then going from MXFP8 to MXFP4 is like a 2x. And then like in total, like you get 8x speed up for on the 5090, but this 8x would be 4x if it's on the 6000 RTX Pro, because the 5090 RTX is actually, as a matter of fact, on consumer GPUs like 4090, 3090, they have very slow FP16 matrix multiplication. So it's twice slower than the normal FP16 speed. So that's why the speed up is 8x here. It should be 4x in theory. So just to summarize, on the B200, for example, or the 6000 RTX Pro, that would be 4x, but the 5090, it would be 8. All right, and I put some resources here. Katla's doc is really great. Really details like all the instructions, and ETX doc if you want to really go crazy and understand like how MMA is working exactly. Obviously Triton, you can find like some examples. So all these kernels that I used here in these benchmarks, they are actually available in Gemlight. And also I would like to give a shout out to Hyunsung. He actually did the integration for MXFP4 support for SM120. Still work in progress, but like, so that's what I used to actually do these benchmarks, because without his work, we would not be able to run the benchmarks on the 5090 RTX. So, yeah, I mean, that's it. Actually, we are exactly on time. I think it's like 1 hour.
Very nice. Thanks a lot. Thanks a lot for the nice presentation. I think it's really nice, and we got into details really quickly. So that's it. I have a couple of questions. So maybe if you have time, we can just take them and, you know, finish like 5 minutes late, kind of. So one question is, CUDA was surprisingly missing from all of this. Is Triton just better user-friendly for low-bit quantization compared to CUDA?
Yes, because in Triton, it makes your life much easier. So you can literally write like a really performant kernel in like half an hour. And if you want to do that, like in CUDA or Cutlass, it will take you probably a couple of days. So we were pushing really big on this because once we have MXFP4 support with NNA, you can literally write any kernel you want. So you can write GMMs, you can write attention, you can write MOEs, but good luck writing MOE FP4 in Cutlass. It's just a nightmare. But like to win it in Triton, it's much, much easier. So I mean, for sure, like, you're not gonna get like 100% performance, but like you would get 90% or 95%, and it's totally fine working with 90%. And you could use your time to do other interesting things than spending 2 weeks just tuning one single kernel. Just my opinion.
Makes sense, I think. So another question is, thank you for the insightful talk, Hicham. I'm curious if there is a repository that models these data types so I could do emulation of these new data types. Please note that I'm still quite new to Triton.
Sorry, I don't understand. Like, you're looking for what exactly? Like a repo?
A repository that models these data types. So I guess MXFP4 or NVFP4.
Yeah. I mean, like, I think it's the gem-like stuff. Like, you can just go through them. Like, they implement everything. So you can just, if you want to learn about it, you can just go through the code. And if you don't understand something, you can just open an issue and I will answer you because I'm maintaining the project. So you can literally just open an issue. Or I think on GitHub, I don't know if we enable discussions. So you can also, maybe if discussions are available, you can also just open discussion. Or if you're on Discord on TPO mode, you can also ask questions there.
Okay. So I write it in the chat. So this is Light, right?
Yeah. So I will put the link. Let me 1 second. I mean the link is in the slides, and we are gonna share the slides. So I'm having a hard time like exiting this full screen. So now it's locked.
There's I know it's fine. Like the person already found it. Okay, I think we are a bit late now, but I think we covered all questions. So like to thank you again, like last time. I think that was really cool. Yeah, thanks for. That's really nice to have like such an expert on this like at the webinar. We will for sure share the slides later, and the recording if that's fine with you, Hicham. And right again for joining.
Yeah, thank you so much.
Thanks a lot also for everyone attending. See you.
See you.